solving quadratic equations by graphing. So we've looked at quadratic equations before in the previous chapter when we factored. So we took an equation, we set it equal to 0, and then we factored it to find the solutions for that equation. So now we're going to start to look at quadratics as a graph, and we're going to look at some other methods of solving those equations. So the first thing we're going to talk about is on a graph, where do we find the solutions? So the solutions, or roots, that's the other word that you'll hear for this, roots, sometimes they're called zeros. So the solutions of the roots of an equation can be found by finding the x-intercepts of the related graph. So we're looking for where this parabola, for a quadratic in this particular case, where the parabola crosses the x-axis. So not the y-intercepts, but the x-intercepts. So I've got three possible solutions here when I'm graphing a parabola. So I could have the parabola crossing the x-axis in two places, in which case I'll have two unique solutions. And we've seen that. We've seen when we have solved a quadratic equation, we've come up with two possible solutions. So here's what it looks like in a graph. We could take that parabola and it could touch upon the x-axis in one place, and we would have one unique real solution. So we come up with one value that is a solution, and we've seen that when we have been solving quadratics. And then we could also come up with no solution. So this parabola might not actually touch the x-axis anywhere. It might be floating either above it or beneath it, and it doesn't actually touch the x-axis, which means there are no real solutions. We couldn't end up with an actual real number solution for that quadratic, and we've seen that too. So this is what this looks like on a graph. Again, we're looking for where the graph of our equation crosses the x-axis, and that's called the roots. You may also hear that called the zeros of an equation. All right, so let's solve some quadratics by graphing. So what we're going to do is we're going to take our equation, and we're going to go through our graphing steps that we've done before. So first I'm going to look for the axis of symmetry by my x equals the opposite of b over 2a. So here for this particular equation, I come up with x equals 1/2. Next, what I'm going to do is, since I'm graphing and I need ordered pairs in order to graph, and I can't come up with ordered pairs from this equation because it only has one variable, I'm going to set, since this equation is equal to 0, which we should be used to at this point, we want that equal to 0, I'm going to take out the 0 and replace it with y. Because what I'm really looking for is I'm looking for when that output is 0. So if you think about your x-axis, your ordered pairs on your x-axis, y is 0. So I'm looking for 0, but I need to find what more output values are so I can actually create a graph. So I'm going to replace that 0 with a y. Then I'm going to take my axis of symmetry, plug that into my equation, and find the vertex. So next I'm going to find the vertex. So for this particular equation, I come up with a vertex. It's not really pretty. Negative 12 and 1/4. So my vertex is 1/2, negative 12, 1/4. This vertex is a minimum. Since my a is a positive, that means I've got that smiley face there. So the vertex is on the bottom, so I've got myself a minimum. So next I'm coming up with a table. So I'm going to take my vertex, I'm going to plug it into the middle of my table here, because I want to come up with two symmetrical sides, less than and greater than my vertex, my x values of my vertex. So this is 1/2 here. Now I really don't feel like putting fractions into this equation. Ugh. So I actually would like to use integers. I just need to get a little creative here. Remembering that we want to work symmetrically away from the vertex. So I want to keep some kind of a pattern there that's nice to work with, but it's symmetrical. So what I did was I went 1/2 less than my vertex, my x 1/2, to get to 0 till I got to an integer, and then I counted by ones after that. So I counted by 1/2, and then I counted by ones after that. So what I need to do for my x's on the other side, my x's that are larger than 1/2, is I added 1/2, and then counted by ones after that, so that I have x values that are symmetrical, but most of these are nice integers, which just makes them friendlier to work with, because then I can do them really mental math. So I'm going to do the positive numbers here, just because I don't want to get into the negatives here. So working with my positives, if I put 1 in here, I have 1 minus 1, which is 0, minus 12, that gives me negative 12. If I put 2 into here, 2 squared minus 2, 2 squared is 4 minus 2 gives me 2, 2 minus 12 gives me negative 10. If I plug 3 in here, 3 squared is 9, 9 minus 3 gives me 6, 6 minus 12 gives me negative 6. And then if I plug 4 in here, 16 minus 4 gives me what is 16 minus 12, and then 12 minus 12 gives me 0, so I have an output of 0 there. So then what I did was I kind of mirrored that on the other side. Since I know these are symmetrical, I can make my y values, my output, symmetrical also, and then I'm going to graph it. So once I graph this, I realize that this parabola crosses the x-axis in two places. It crosses it over here at -3, and it crosses it at 4, which I can see from my table because my y values are 0. Remember, originally I took the y out and put the y in where the 0 was. So I'm looking for where y is 0. That's my roots. So I have two solutions, -3 and 4. Now, kind of backtracking here, I could have solved this by factoring, and that's the solutions I would have come up that way also. All right, let's look at two more solving equations by quadratics by graphing. So let's look at x squared minus 4x plus 5 equals 0. So again, I'm going to go through the same steps of graphing a quadratic function. I'm going to start by finding my vertex. So my vertex here is x equals 12. 12, x equals 2. I have x equals 2. I'm going to take my equation, I'm going to replace the 0 with a y, and now I'm going to give myself some inputs and outputs. So I'm going to take my axis of symmetry and plug that in for my x value. So I plug that in and I get with an output of 1. So my vertex is 2, 1. I know this is a minimum because my a value is positive, so I know my parabola opens upwards. My vertex is at the bottom, so this is a minimum. Now I'm going to create a table. Here's my minimum at the middle, and I subtracted 1 repeatedly and then added 1 repeatedly to get two symmetrical sides of my x values, because again my parabola is symmetrical. And then I did some mental math in my equation to figure out what my y values were. So 1 minus 4 gives me -3. -3 plus 5 gives me 2. If I plug a 0 in here, I get 0 plus 5, that gives me 5. If I plug a -1 in here, that is 1 plus 4, which is 5. 5 plus 5 gives me 10. And then I mirrored those on the other side, and then I graphed. You will notice that these numbers start above the x-axis and then keep getting higher. And we talked about the vertex was at the bottom, so we knew this opened upward. So since this starts above the x-axis and it opens upwards, it's never going to cross the x-axis, so it ends up floating up here, which means that there is no solution. All right, one more. Let's take a look at x squared minus 6x plus 9. Again, same steps. I'm going to start by finding the axis of symmetry, x equals 3. Next, I am going to substitute 0. I'm going to put y in place of the 0. And I'm going to find the vertex. So the vertex is 3, 0. The vertex is 3, 0. My a value is a 1. So again, this is a parabola that opens upward, which means my vertex is a minimum. So I've got 3, 0 is at the bottom. So then I'm going to create a table. 3, 0 is at the middle. I've gone symmetrically on either side, below and above 3 for my x values. And I did some mental math there to get my y values, and then I plotted them. So you'll notice this graph, the parabola, only touches the x-axis in one spot. So it touches it here at x equals 3. So that is actually the only solution to this particular quadratic. And you'll notice this is actually a perfect square trinomial. So if we had factored it, we would have factored it and come up with only one solution. So that makes sense whether we talk about factoring or graphing. So looking at parabolas and graphs of quadratic functions to find solutions, and there's the same 3 possible opportunities for things to happen as there were when we factored. We could come up with 2 solutions, we could have 1 solution, or we could have no solution at all, and each of those depends on what the